So we've seen that when we're trying to understand how ionic compounds form from their elements, electrons are transferred. For example, if you look at a sparkler that's producing really brilliant white sparks, one of the metals that they can put into the sparkler is titanium, Ti. It can react with oxygen, and it can give you this compound. We're going to learn that that's called titanium 4 oxide later. But you got a metal here. Metals have low ionization energies, right? So they give up their electrons easy. So this wants to give up some electrons. Nonmetals will gain electrons very easily. They have high electron affinities. So these two get together and cooperate. And in the process, it releases a tremendous amount of energy. If you look at a sparkler, you can see the energy being released as photons, as light, and as heat as well. And they form this compound. Now let's try to figure out what's going on. How is this an electron transfer? I don't see any electrons in the reaction, the way it's written. How can I take this reaction and show the electron transfer? That's what we want to do right now. And one of the thing that loses electrons is going to be the oxidation, and the part of the reaction that gains electrons is going to be the reduction. Now, we talked about that a little bit in the last lesson. So, all right, well, how about if I look at the titanium separately from the oxygen? I write two reactions, one for the titanium and one for the oxygen, that shows the titanium losing its electrons, and then another one that shows the oxygen gaining electrons. All right, first I have to decide what are the charges of the atoms that are inside this compound. What ions are in there? Well, I can get the charges of the common ions from the periodic table fairly easily. Now, so far I've taught you that an element will gain or lose electrons until it gets the same configuration as the nearest noble gas, right? That was the big idea in some of the work that we did previously. So if you've got oxygen, it wants to be like neon, which is the nearest noble gas, and it will gain 2 electrons to be there. So if oxygen gains 2 electrons to be there, then each oxygen here is going to be an O-2, because you want them both to be satisfied, right? They both want to have a neon configuration. So there are 2 oxygens in there, and each one's going to have a -2. Now what about the titanium? What about the titanium? Well, it's over here. Is it really going to go for the nearest noble gas? It has to go all that way to get to krypton. Is it going to go this way? Well, maybe. I guess it could go for argon. You would think it would go 1, 2, 3, 4 electrons to get to an argon configuration. But when you're in the D block, and that turns out to be what it's doing here, but when you're in the D block, you can't always do that. You can't always go for the nearest noble gas. And that means you can't tell ion charges for D block elements from the periodic table. Let's write that down, because that's something that you're going to want to be able to do, but you can't. You can't always tell ion charges for D or F block elements. Watch out for that. You can't do it. I can tell everything in this first column is going to lose 1 electron to get like the nearest noble gas. So everything in this column will form +1 ions. Everything in this column will form +2 ions. Everything in this column will form +3 ions. Things in this column tend to form covalent molecules. When they do form ions, they can form +4 ions. Now, when you get to the nitrogen column, it's easier for them to gain electrons. So the nitrogen can gain 3 electrons. So everything in this column tends to form, well, all the nonmetals in this column tend to form -3, -2, -1. So negative charges are for the nonmetals in these columns. Positive charges are for the metals in this column. For example, lead can form a +4 ion. Tin can form a +4 ion. Even germanium, but germanium is a metalloid and it kind of shares. So these things don't form ions at all. Carbon, silicon, and germanium tend not to form ions. They tend to share their electrons instead. Anyway, remember, here's the borderline that we're talking about here. I'm assuming you know this by at this point. And we usually, sometimes, most books will extend the borderline down that way. Anything to the left of this is a metal and will form positive ions. Anything to the right of this is a non-metal and will form negative ions. All right, so that's just a quick primer on ion charges. This all goes with counting to the nearest noble gas. You can't tell the ion charges when you're in the D block or in the F block either. You can't tell when you're down here or up here. All right, so keep this in mind. We're going to actually use it in this lesson and the next lesson quite a lot. All right, so I can't tell from the periodic table. So how can I figure out the charge on the titanium? Well, the entire titanium for oxide here, this whole unit here is going to have to be electrically neutral. So if the oxygens are contributing -2 and -2, that's a total of -4. So the titanium must be contributing a total of +4. So I can figure out what the charges are in the formula that I have here, the ionic compound that I'm forming here. And that's going to help me figure out where the electrons are going. The titanium is going to become Ti +4 on the right-hand side. Now I can't just write this down as a reaction all by itself, because not only do your atoms have to balance on either side of an equation, but your charges do as well. So here I have a +4 charge, and here I have a 0 charge. There's no charge written in. So if you don't have a charge written in, it's 0. So I have to balance this, and what's happening is that this is spitting out 4 electrons. So I'll write 4 electrons in there, E-, my symbol for electrons, everybody's symbol for electrons. This is the oxidation. We did this before, but it helps to go over it again. Oxidation is when the charge goes up. And it's also when you lose electrons. So for this titanium, its charge goes up when it reacts. It also loses 4 electrons. So that's how I can recognize that this is an oxidation that I have here. Now let's do the other half of the reaction that involves the oxygen. The oxygen is going to turn into 2 oxide ions. That's what these O-2 ions are called, oxide ions. We'll learn to name them later. Now this isn't charge balanced either, is it? Because here I have 2 -2 charges for a total of -4 on this side of the equation. So I must have a -4 charge on this side too. There are 4 electrons that the O2 captures, and it becomes then the oxide. This is a reduction. In a reduction, the charge goes down, the charge is reduced. How does the charge change? It goes from 0 to -2. So it's going down. And you're gaining electrons here. So keep these two terms straight: oxidation and reduction. We can write these two half reactions that show us the oxidation and reduction separately. But when I add the two reactions together, I'm going to get a total reaction with titanium on the left side, 4 electrons on the left side, O2 on the left side. And on the right side, I'll have a titanium. Here, let me write it down. On the left side, I have, and now on the right side, I'm going to have, when I add these two reactions together, I'm going to have titanium with a +4 charge, +4 electrons, plus 2O-2. So if I look at that, I can see that there's 4 electrons on either side of the equation. And just like an algebra equation, if you've got the same thing on both sides of a chemical equation, they can cancel. So really, here's my reaction. And what I've done up here is I've put together the titanium +4 ion with the two oxide ions, the 2O-2 ions, to form that, to form TiO2. All right, let's do another one like that. How about this? Now, you can actually make hydrogen with a lot of different metals, as long as it's an active metal. You have an acid, and this is hydrochloric acid. But if you have it work on metal, it can produce little bubbles of hydrogen. And in fact, you can get aluminum and get this to work with it too. You'll get aluminum chloride in there, but you'll get hydrogen gas out of it. And it is an easy way to make hydrogen. All right, so let's figure out what's going on here. This is a redox reaction, and here's how I can tell. If I assign charges to all of the atoms in this reaction, I can see that the charges on some of the atoms change. Anytime the charge on an atom changes in a reaction, and I'm going to start using, and you're going to see me do it, I'll do it without even thinking about it sometimes, so I might as well introduce it here. I have an abbreviation, and chemists have an abbreviation for a reaction. They don't like to write the word out all the time, so RXN is shorthand for reaction. So if you see me writing that, that's what I mean. Anytime the charge on an atom changes in a reaction, you can say it a couple different ways. Electron transfer. You can say you have redox, that's oxidation reduction. Or you can say I have an oxidation reduction reaction. So just some vocabulary here. So what you're looking for here is what the charges on all the atoms in a reaction are, and that will let you track where the electrons are coming from and where they're going to. So let's try to do that. Let's try to assign all the charges on these things. What's the charge on this? Well, it doesn't have a charge written down there, so I'm going to say it's 0. Let me put the charges in a different color. That's got a 0 charge. Now how about the atoms in the HCl? Well, we can take a look at that little ion chart that we just made up in the on the periodic table, and that'll help us there. I recognize there's a chloride ion in there. It's got a -1 charge, and there's a hydrogen ion in there. It's got a +1 charge. So I can assign charges here. Okay, now let's look at the charges on the other side. What have I got going on here? Well, this is an ionic compound. It's made of magnesium ions and chloride ions. It's got a metal and a nonmetal, so I recognize it as an ionic compound, and I recognize those then as ions in there. Now, if you had all nonmetals here, you would say that's not an ionic compound. And at this point, we don't know how to put charges in for those. But when it's a metal and a nonmetal, I am allowed to put charges in from the periodic table if I can. And if I look at where magnesium is, it's +2. And if I look at where chlorine is, everything in this column wants to gain an electron to be like the nearest noble gas. Chlorine is here in the -1 column. So I can write +2 is the charge on the magnesium, and -1 is the charge on each of the chlorines. Now, this makes sense, right? Because if you've got 2 chlorines in there, and each one has a -1 charge, that's a total -2 charge, and it balances this off. So you've got to have the charges balance in the formula for an ionic compound. Okay, what about this? There's no charge on this showing, and you could say, well, maybe one of the hydrogens is a +1 and the other one's a -1. But why? You know, why would one hydrogen be different from another? These 2 hydrogens have to be identical, and their charge has to add up to the total charge, which is 0. So the only way you can get that to work is to put a 0 charge on there. In fact, anytime you have an element, there's a 0 charge on it. So if you've got an element all by itself, there'll be a 0 charge. So here are all the charges, and this is going to help me write the 2 half reactions down. Okay, let's write one down for the magnesium. The magnesium starts out having a 0 charge, and it goes up to a +2 charge. All right, so what's going on there? Is this right? It's not charge balanced yet. I have to add something to it. There's a +2 charge on this side, but there is a 0 charge on this side. Both of the sides have to have the same charge. What I can do at this point when I'm writing these half reactions down is add electrons to one of the sides to balance the charge off. Obviously, I can't add electrons over here because this is a plus charge and this is a 0 charge. If I add electrons over here, I'd be putting a minus charge on one side and a plus charge on the other side. I'd be making things worse. Okay, now what is this? An oxidation or a reduction? Well, we said that if the charge goes up, it goes from 0 to +2, then you have an oxidation going on. So that's the oxidation part of the reaction. Okay, what if, how about the other part? Well, let's just look at the hydrogens. Because if I look at the chlorines, what's happening with them? They're -1 on the left side and -1 on the right side. So I don't really have any change in the chlorines. And in fact, the chlorines are not really participating in this reaction. It's the hydrogens and the magnesiums that are doing all of the action here. Okay, so I can look at this. I can write it down like this if I want to. I could write it down like this. I can also write it down without the chlorines in at all because they're not really doing anything. And what's going on here? So I could write it down like this. That's okay. You could do that. Or I could write it down without the chlorines in it at all. There are two H pluses in there. And I can go over here to H2. Doesn't that look simpler than this? So if the chlorines aren't doing anything, you can kind of leave them out. We're going to talk a lot more about this business later on in a future chapter. So if you're not getting like how I'm leaving the chlorines out here, don't worry. We'll come back to this later. I could write it either way. What I just erased was just as right as this, but this is simpler, and simpler is better, right? So I've got 2 plus charges on this and a 0 here. Where do I add the electrons? Well, I can't add them to this side because it'll make things even worse. I have to add them to this side. I have to neutralize those positive charges to get a 0 charge here. Now what's happening to the hydrogen? It goes from a +1 charge to a 0 charge. So its charge is going down, it's being reduced. This is the reduction reaction. Now if I put these two reactions together, if I add the oxidation and the reduction together, I'm going to get what? Magnesium plus 2 H pluses plus 2 electrons gives me magnesium plus 2 electrons plus H2. I didn't bother to write the electrons down here because they cancel. There's 2 electrons on the left, 2 electrons on the right. You can cancel them out. So this reaction here that I've written is kind of the heart of this one up here. This is essentially what's going on. The chloride ions are just in the background neutralizing some of these charges. They don't actually participate in the reaction, so I can write the reaction down this way, or I can write it down this way. Either one is correct. This way has less, it's simpler, there is less extra information that I don't need in there. Now I want you to be able to do this for some simple reactions that involve combining 2 elements. All right? And if you're combining 2 elements, it is fairly easy for you to figure it out using the periodic table. So look at that, and we're going to want to go a little further with this in the next couple videos. Let me show you where we're going with this. Anything that burns, any reaction where something is burning, is an oxidation reduction reaction. So if you're taking, say, natural gas and you're burning it in oxygen, that is going to give you carbon dioxide and water. This is a redox reaction. I better balance it, right? If I put a 1 in front of the CH4, there's 4 hydrogens on this side, so I'll need to put a 2 there. Now, if I put a 1 in front of this, there's 1 CO2 there. So this side is all nailed down at this point. How many oxygens on this side? Well, there's 2 here and 2 there, so I better put a 2 there. Now it's balanced. Okay, if this is a redox reaction, I want to see where the electrons are coming from and where they're going to. But wait a minute. These are not ionic compounds. There are not ions inside of there. None of these things are really ionic compounds. They are all covalent compounds. So I can't assign charges because I don't see any ions in there. You might say, well, look, you can look at this on the periodic table. You can say, well, oxygen is -2 and hydrogen is +1 from the periodic table. You can say oxygen is -2 here, so, and carbon is +4 from the periodic table. This would be 0. Hydrogen would be +1, and carbon would then be what? -4. So you get something kind of fun going on here. Where if you put a +1 on for the hydrogen, you're getting a -4 for the carbon. Turns out you can do that. Turns out that that's right. But these are no longer really charges that we're talking about here. In a covalent compound, you don't have ions. But you can assign charges to see where the electrons are going from. Let's call them effective charges for tracking electron transfers. We'll call them, we won't call them charges, right? We'll call them this. Well, that's kind of a long name. Why don't we call them oxidation numbers? That's what we'll call them. Oxidation numbers are the fake charges that we're going to assign to covalent compounds, well, and ionic compounds too. We can assign them to any compound. When we're assigning them to ionic compounds, they're actual charges. When we're assigning them to covalent compounds, you can think of them as those are the charges the atoms would have if it were ionic, but it's not. Okay? Now, I have a step-by-step procedure for assigning oxidation numbers. And we'll look at that in the next 2 videos.